Dear participants, we'll have the second session. Today we have Ms. Athulya from Walmart for the second session of today's FDP. I would like to give a brief introduction about Athulya. She is basically a geotechnical engineer from IIT Mumbai, but she switched on to data as a data scientist to Walmart. And she's a dynamic data scientist renowned for driving transformative initiatives and shaping product strategies through data-driven insights. Her career is a testament to her leadership and strategic vision, exemplified by her impactful role at T-Mobile, where she spearheaded the development of predictive analytics model to optimize network spectrum management within the advanced 5G infrastructure. Through her work, Athulya played an important role in shaping the company's strategic direction for network enhancements. By analyzing 5G network performance data, she identified key opportunities for improvement, resulting in significant advancement in robustness and reliability efforts that bolstered T-Mobile's position as a leader in the telecommunications industry and directly influenced the critical product strategies and decisions. Collaboration is central to Athulya's approach. She has excelled in bridging the gap between engineering, product, and data science teams, ensuring the seamless translation of insights into actionable strategies that drive measurable outcomes. In essence, we can say Athulya's leadership, strategic acumen, and collaborative spirit have been instrumental in fostering innovation and steering product strategies in dynamic, fast-paced environments. So with this small introduction, I would like to invite Ms. Athulya. Welcome you, ma'am. Your mic is on mute.
Yeah, are you able to hear me now?
Yeah, it's audible now. You can proceed, Athulya.
Yeah, okay. Thank you so much, Lavanya. Let me share my screen. Give me a second. I think I need to quit and rejoin because of some screen sharing policy. Let me do that first. AI techniques in causal analysis, and also cover a few case studies and conclude the presentation with some challenges in causal inference and best practices. So before going to say what is causal inference, I'll start with why causality, why causal inference matter. So from the evolution of human era, like human are always asking the question why this is happening. So why wildfire happening in LA? Why there is always a flood happening in Chennai during monsoon season? So all these questions are started like the human intuition about answering, identifying the why behind every action. So here also we are in causality. Also, people are understanding why behind each action, why it's causing. So what is the cause of all this action? The why behind everything action is identified through the causality. So, in terms in the context of a sustainable urban growth, so why causalities matter, and where we can use this causality to better understand the sustainability plan in urban growth. So, uh, causality can be used in optimizing urban plan decisions. For example, like if you want to understand the importance of green spaces, how green spaces is affecting the livability of that urban space, how green space is affecting the happiness index. So whether the green space is actually causing people in that city is more happier. So this kind of question we can answer through the causal analysis. Another example is the evaluation of mobility policy. For example, like a public transportation, whether the public transportation in that city is effective, whether that's actually helping to reduce the traffic congestion. And also we can answer some questions like electric vehicle adoption. Does the electric vehicle adoption actually reduce the carbon emission, or it's actually good for sustainable growth? So the causality behind these kind of questions we can answer through causal inference. Another example is the impact of new bike lane. So if you introduce a new bike lane to the city, does that affect the traffic at that traffic pattern? Does the traffic congestion is reduced because of the new bike lane policy? So the causal inference will answer these kind of questions. And also when we talk about the sustainable growth, we can also measure something like carbon reduction. Does carbon reduction help the livability? Does carbon reduction help to decrease the mortality rate in that urban? So all these kind of questions we can answer the causal inference. So that's why the causalities play an important role in sustainable growth. So now coming to the question, what is meant by causal inference? What is this causality? So I'll talk about some foundations of causal inference here. So in a technical term, we can say that causal inference is the understanding the cause and effect relationship. Causal inference is the process of determining whether how one variable that causes directly influence the other variable, the effect. So beyond a correlation, it helps to understand does the X causes Y rather than X and Y are related. So when we talk about the EV vehicle adoption, so does the EV vehicle adoption causes the decrease in the environmental pollution? So it's not direct telling whether EV vehicle adoption is correlated with the environmental pollution. It's making understand whether that causes the uh, decrease in the environmental pollution. So this is cause and effect relationship is called understanding cause and effect relationship is called causal inference. So I'll go over a video or like intro video about how
The Stanford one-year master's in management has really accelerated.
Is a causal
So please let me know if you're able
similarities
to
and
see
differences
the video.
between correlation, regression, and causality. And as always, let's get right into it. As you already know from our video on correlation, correlation analysis examines the relationship of variables. But beware, later in this video, we will discuss in detail why a correlation does not necessarily mean there is a causal relationship. One question might be, is there a correlation between the age at which a child speaks his or her first sentences and the later school success? If the correlation analysis shows that the two characteristics are correlated, we could now investigate whether there is a causal relationship. If there is a causal relationship, school success could be predicted by the age at which a child speaks his or her first sentences using a regression. So the question now is, do we have a causal relationship in our example? In this case, the answer is very easy because we have a temporal separation. If there is a correlation between the age at which a child speaks his or her first sentences and the later school success, it is clear that the time at which a child speaks his or her first sentences influences later school success and not the other way around. Later school success cannot influence the age at which a child speaks his or her first sentences. But beware, it's not always that easy. Let's look at the next example. Let's say at the end of the school time, you make an intelligence test with pupils and ask them about their high school grade. After you've conducted your survey and you're analyzing your data, it will surely turn out that there is a correlation between intelligence and the high school grade. But now comes the big question mark. Is there a causal relationship? Of course, we could now simply set up a regression model and define intelligence as an independent variable and high school grade as our dependent variable. Then we could predict the high school grades by using intelligence. But this is not a proof of causality. I think now we can look at what causality means and under which conditions one can speak of causality. Causality means that there is a clear cause-effect relationship between two variables. A common mistake in the interpretation of statistics is that when a correlation exists, it is immediately assumed to be a causal relationship. Here I have a suitable example for you. The American statistician Darrell Huff found a negative correlation between the number of head lice and the body temperature of the inhabitants of a group of islands. A negative correlation means that people with many lice generally have a lower body temperature than people with few lice. And now the interpretation of the inhabitants. The inhabitants of the islands concluded, since lice reduce fever, they are good for health. So their assumption was that head lice have an influence on the body temperature. In fact, the right conclusion is the other way around. An experiment could prove that high fever drives away the lice. So the high body temperature is the cause, not the effect. Therefore, one cannot speak of a causal relationship just because there is a correlation. For causality, there are exact preconditions. But what are the conditions for causality? When can we speak of a causal relationship? There are two conditions for causality. First, there is a significant relationship, that is, a significant correlation. This precondition is, of course, quite easy to test. We simply take the correlation coefficient and check if it is significantly different from 0. The second condition can be satisfied in two ways. First, it is satisfied if there is a temporal ordering of the variables. So variable A was collected temporally before variable B. Furthermore, the second condition can be fulfilled if there is a theoretically founded and plausible theory in which direction the causal relationship goes. If neither of the two is true, which means that there is neither a temporal order nor can the causality be justified by a well-founded theory, then we can only speak of a relationship, but never of causality. Thus, it cannot be stated that variable A influences variable B or vice versa. Let's take a look at our examples again. In the first example, where the question is whether the age at which a child speaks the first sentences influences later school success, there is clearly a temporal component. The measurement of when the first sentences were spoken is clearly before the measurement of later school success. The relationship cannot be the other way around. If one has a great school success by a lot of studying and support, this has of course no influence on when the first sentences were spoken. On the other hand, if we measure intelligence and the high school grades at the same time, we do not have this temporal component. In order to be able to make a statement here, we have to look for a well-founded theory of which variable influences which one. If no such theory exists, no statement about causality can be made. There is certainly a high correlation between intelligence and high school grade, but it could also be that people who study a lot, have good grades, and have acquired their knowledge to do well in an intelligence test. So in this case, the intelligence and the grades were determined at the same time. Of course, you can avoid this by taking the intelligence test before school starts. Then you can be sure that the school had no influence on the intelligence test. For sure, this requires a lot of time and effort because you get the results many years later and the same people have to be interviewed at 2 different times. Now you have a good overview of what causality means, and we can go into more detail about regression. Check
So now you got some basic understanding about causal inference. So let's go over some foundations and terminologies of causal inference. So when we talk about causal inference, these are the terminology that we normally use. So the first word is treatment. We notated it as a T. So it refers to as a intervention or action being evaluated to determine the effect. For example, when we talk about the electric vehicle case or the introduction of new bike lane, then that introduction of the new bike lane is called treatment. When we talk about electric vehicle adoption, the adoption of the electric vehicle is the treatment here. And it's help to what is the purpose of defining the treatment, because it's help to assess the effect of intervention, and this treatment is also called as intervention. The action that we are taking, that is called intervention, and the measure of that action is called treatment, and it is denoted by, normally it's denoted by the notation called T. And the next terminology is outcome. We denoted as Y, and it is the definition of the measure of the results. The effect, how the effect is measured, the measurement of effect is called outcome. And an example, in the example of bike sharing, the outcome could be the reduced traffic congestion, or it can be reduced the lower carbon emission. Whichever the outcome of our interest, that the measurement of that is called outcome, and that is denoted as Y. So once we identify the treatment and once we identify the outcome, we can understand how the treatment is affecting the outcome. And also there is another factor that is called confounders. It's sometimes denoted as X, sometimes denoted as C. And this is the confounder variable that influence both outcome and treatment. So some set of variable that has some spurious correlation with both treatment and outcome. For example, in context of like the bike sharing, the weather condition may affect the like influence of adoption of both bike steering. Also, the affects the in traffic congestion. For example, like extreme weather condition, like people won't use bike and they won't like travel much. They won't use their car much. So both traffic congestion and bike use also both are reduced because of the weather condition. So then that scenario we call weather as a confounding factor. And another factor like confounding factor we can, for example, the population density. Higher population need more congestion and more adoption of bike sharing program, and vice versa. Lesser population may lead to lesser traffic congestion and lesser adoption of the bike sharing program. So we need these factors to understand how these confounding variables affecting both treatment variable and the outcome variable. Then only we can understand the pure causation between the treatment and the outcome variable. And to understand the relationship between both treatment and outcome variable, that is called the causal inference. And the golden standard for doing the causal inference is called randomized control experiment. In online world, it's called A/B testing. So like in randomized control trial or A/B testing, what we are doing is like we randomly select some population A and B and comparing the effect of like how the changes in A causes the outcome and how changes in B causes the outcome and comparing both. So this is the golden standard because like it gives the better biased estimate for the our causal effect of the treatment. And so I'll show you a video. This video explains the what is mean by A/B testing and some of the assumptions in causal inference and some example scenario.
Get now. The time to get reliable internet with everything you want is now.
Hello, everyone, and welcome to a special episode of Code Emporium where we are going to talk about causal inferencing. I'm not going to be showing my face in this video because there's some technical detail that you don't need to be distracted by my face for, and so we'll get to it. But before that, please do hit that like for content like this. Please join us on Discord because we have a Discord server. Links are down in the description below. Do be a part of the community, and we would love to have you. Subscribe for more, and let's get back to the video. Before talking about causal inferencing, we need to talk about randomized controlled tests. We call these A/B tests in the industry, but I'll use randomized controlled tests here since each term makes more sense. I own an e-commerce store and I want to send out emails to individuals about our products, hoping that'll increase purchase conversion. But I don't know if these emails are going to help or hurt. And so I want to test this out with a randomized controlled test. This involves 5 steps. We first select the users to participate in the test, and ideally you'll select them based on a uniform criteria. Then we split these users into 2 groups evenly, and then we give one of the groups the emails and don't send the other group any email whatsoever. And then we monitor the purchase conversion for each user over time. And once the experiment is complete, or once the test is complete, we make decisions like, yes, the emails increase purchase conversion, or just the opposite. Now let's break down the phrase randomized controlled test. We're selecting users at random to be a part of the control group and the treatment group. This is because the only difference that we want between these two groups is just the fact that one receives emails and the other does not. If we quote unquote control the effects of other variables through randomization, we can then be confident that if the experiment says that sending email increases purchase conversion, then it is almost certainly true that sending emails indeed causes purchase conversion increase. And that's kind of why randomized control tests are so important, and they can also be used for inferring causality. But there are many situations that we just cannot run these randomized control tests. One is that, well, setting up the experiment might be impossible. For example, instead of testing the efficacy of emails, what if I wanted to test the efficacy of billboard ads for my products? Now, you can't just randomly go to cities and set up billboards just for the sake of a test, and so this test setup is impossible. And another reason where we can't use these RCTs is because the experiment takes too long. And in order to combat this, it makes sense to make inferences based on historically observed data. So in this sense, we don't need to set anything up because the data already exists, and we also don't need to wait for any experiment time. Now, this is great, but observed data is messy, and randomized controlled tests are cool because we can control for variables that can affect our causal inference. And so if we're going to perform causal inferencing on past data, we need to be able to somehow control for the other factors that plague the observations. Let's talk about three main challenges to causal inferencing. The first is confounders. I'm going to take a medical example for this. So the flu is a problem for the world, and I developed an elixir that should cure the flu. But before releasing it to the public, I want to run a clinical trial. Now, this test isn't really hard to set up, and it's also not going to take an obscene amount of time, and so I can actually run an experiment or a test for this. So I take some users who have the flu and tell them to use the elixir, and they are my treatment group. And then I take another set of users who have the flu and give them a placebo, or rather just not treat them. And this is my control group. After a few weeks, I see that the number of people in the treatment group that recovered from the flu is way better than that of the control group. Now, this means that the elixir is actually working and causing the flu to go away, right? Well, not necessarily, because if we look at the experiment closely, I see my control group has an average age of 65, while the users in my treatment group have an average age of 35. This means that the people in the treatment group probably could have recovered on their own, even without the elixir. But this test doesn't definitively prove that is the case. And in this example, age is a confounding variable. It's a variable that we haven't controlled for and that can have some causal effect on whether a person recovers. And this is exactly why when conducting A/B tests, we randomize in order to make sure that the age and also the other potential confounding variables are equal between the two groups. But like I said, in many cases, we cannot conduct a trial like this. And so confounding variables is a challenge in causal inferencing that uses prior data. You need to be vigilant of these confounders and control them too. Now, the second topic that I want to talk about is selection bias, and confounders actually very well segue into this topic. So selection bias occurs when a group of users chosen for the treatment group isn't a good representation of all users in the population. This is exactly the case where the treatment only represents young people and is not really representative of the population. And so there is a selection bias here, and we need to account for this when looking at prior data. The third challenge we need to account for is counterfactuals. Facts are truth. Counterfacts are what would have been the case had this person not received the elixir. When using prior data and also conducting a test, we need to compute counterfactuals for each individual. This is done just so that we have an apples to apples comparison. There are a few strategies that we can use to actually calculate these counterfactuals, like machine learning techniques, as well as a technique called matching. We'll take a look at this soon, very briefly.
Most homeowners have it somewhere in their house. It's that one bad window.
Let's now talk about some of the assumptions that we need to make for causality. So first off, why do we need to make assumptions? We want to tailor prior data to make it as representative as a randomized controlled test as much as possible. We need to make assumptions because there will always be some confounders that have some weird and unintended effects on the outcome that we simply will never control for. The assumptions make the problem of causal inferencing with past data possible. So a first assumption here is the causal Markov condition. When doing causal analysis, we need to talk about causal graphs. Causal graphs are graphs with directed edges that show causation. For our medical example, we have a graph that kind of looks like this, but this is kind of convoluted. And so to simplify the causal graph to be a directed acyclic graph, we have confounding variables that have direct causal effect on the treatment and sickness outcome. And the treatment itself has an effect on the outcome, but there's nothing more than this. Another assumption that we make is SUTVA, which is a stable unit treatment value assumption. A sample in the control group doesn't affect the samples in the treatment group. That's basically what it says. This assumption is required to prevent any interaction effects. And for our medical example, this is true. We don't have people who receive the elixir influencing the people who don't have the elixir. And the third assumption that we're going to make is ignorability. This assumption says that there exists no additional confounders that has an effect on the treatment and the output. This is an extremely important assumption. Otherwise, even if we see the treatment group doing better, we wouldn't be able to pin a cause, since the cause for getting well or getting sick could be pinned on potentially an unmeasured confounding variable. And so we assume we have no missing confounders. Since this is such a super important topic, I'm going to link more details down in the description below on a discussion in Stack Exchange. So do check it out if you are interested in some more details. All right, so now let's get on to actually measuring the average treatment effect. Let's say that in our medical case, we want to answer the question, does the elixir make people feel better? We're working with some hypothetical data in this table. The first column is the person. The second and third columns is whether the person got better or not better, depending on whether they received the treatment. And so we only see one of these two columns being populated for a given sample. Ajay received the elixir and got better. Sam didn't get the elixir and also got better. The simple solution to answer the question, does the elixir make people better, would be, first of all, let's count the people who got the elixir and who also got better and divide it by the total number of people who took the elixir. This gives us 0.6 in this case. Next, we count the people who didn't get the elixir who got better and divide it by the people who didn't get the elixir, which is 0.4. And then we subtract these numbers and this yields a positive 0.2. So overall, this looks like the elixir has a positive effect, right? But there's a problem here. Let's add a column for age. Well, looky here. Looks like the average age for those who received the treatment is 48, while that of the control is only 29 and a half. Now, that's a big enough difference that age could potentially be causing some effect on the output. And so, like we mentioned before, age is a confounding variable. To solve for this problem, we need to determine the counterfactuals for every person taken into account. And so we need to determine the spaces. The counterfactuals essentially say, for the people who received the elixir, would they have gotten better without it? Also, for the people who didn't receive the elixir, would they have gotten better with it? One way to do this is by matching. Essentially, you have to try to find people of the same age who received the other treatment and use that as the counterfactual estimate. So in this example here, Sam and Rondo are the same age and they receive different treatments. So if Sam received the treatment, we might see something similar like we did with Rondo and also vice versa. And this kind of makes sense. Another slightly more complex way that we can fill these spaces, that is determine the counterfactuals, is by using machine learning. That is like building a model that takes an age and treatment as the input and then predicts the output. We train it on factual data and try to predict the counterfactuals. I'd like to go over these two techniques probably a little more in a separate video. But for now, whatever technique we use, let's say the counterfactuals are populated as shown in red. To determine the average treatment effect, we subtract the case where the person got or would have gotten the treatment with the case where they had not gotten or would not have gotten the elixir treatment. This number is going to be the individual treatment effect, and we calculate this for every single individual. We then take the average of the individual treatment effects to get the average treatment effect. Now, this final value is plus 0.1. So it looks like the elixir does indeed help even when accounting for age. Now, if I'm just looking at this one number, I would probably make a policy that says for everyone who has the flu, let's just give them the elixir. Now, let's just see how true this actually holds up. So we have age as a confounding variable, and now let's determine the average treatment effect, which is conditioned on age. And this is known as the conditional average treatment effect. So the Kate will help us answer, how does the elixir affect people over the age of 35? And how does the elixir affect people under the age of 35? So for this, we would just average the individual treatment effects for those values of age greater than or equal to 35, and then also those values that are lower than 35. So the conditional average treatment effect, where the age is greater than 35, is a positive 0.4. And that which is lower than 35, it's a negative 0.2. Hopefully the simple algebra is easy to understand here. So it's clear here that the treatment affects different age groups differently, and this is what we call treatment heterogeneity. And so, based on the assumptions that we made on the causal graph, and based on the Kate values that we are seeing here, we can conclude that this elixir indeed does help older people or older patients get better from the flu, but it doesn't seem to have a positive effect on younger people. So now looking at all of these values and based on all of these constraints, I would only prescribe the elixir to older people who have the flu and just let the younger people recover on their own. Note that we determine all of this without actually conducting a randomized controlled test, and it's purely based on past observed data. All right, so lots of things in this video in a short amount of time, so let's summarize what we did here. We first introduced randomized controlled tests and why we cannot always perform them, and hence we try to use causal analysis and causal inferencing that simulates randomized controlled tests based on past data. We then talked about the challenges in trying to make the past data behave as a randomized controlled test, like the presence of confounders, which leads to selection bias, and also the need for counterfactuals. Then we talked about the assumptions required for causal inferencing, and with a medical example, we showed how to determine the average treatment effect to definitively prove that a treatment has an effect on the output. And then we also looked at the effect of the treatment conditioned on different age groups to make better decisions. That's all we have for this video. There's so much more that I want to talk.
So now, we covered the basics of fundamentals of causal inference. What are the terminologies used in causal inference? So let's move on to how we can use this technique, how to determine the causality. So what are the EA techniques that's available for causal analysis? So in the previous video, we already seen a methodology called propensity score modeling. So that is like matching the users based on the ML modeling score and identifying the causal effect. The causal effect is also known as average treatment effect that explained in that video called ATE. And if we condition on the confounding variable, then that causal effect is known as conditional ATE. So it's noted at a CATE. So coming to the different causal techniques. So there are like different econometrics techniques that available that uses basic machine learning modeling that models are called propensity score modeling, difference in difference algorithm, regression discontinuity, synthetic control, and instrument variable. And there are like advanced AI model. Based on the advanced AI model, there are like different causal methodology that are like Bayesian causal modeling, causal trees and deep learning modeling, double machine learning modeling, and structural causal modeling. So I'll give you a high-level overview about all these techniques here. So the propensity score modeling is just a modeling based on ML modeling, where we are using set of confounding variables, and using any ML model, we'll predict the score of being getting a treatment. So that is called as propensity score. And using some matching algorithm, we match the control and treatment group to get the matched to mimic the randomized control trial, and we'll finally use their outcome differences to determine the causal effect. So that is called propensity score modeling. There are like two different algorithms in propensity score modeling. One is called propensity score reweighting, and other is called matching. And the second model is the difference in difference. When we have a clear temporal data and we have a like parallel trend between that outcome of different temporal zone, then we can use this algorithm. It's called difference in difference, which actually like on high level, which actually comparing the different tempo like post-treatment data average with pre-treatment data average, and compare it with for both treatment and control, and getting the estimate. So I'm not going in much detail about these algorithms. I'm just giving high level. And another one is the regression discontinuity, where if a intervention, the action that causes a is also associated with a temporal factor, then we can use this regression discontinuity, where we'll using a regression model, ML-based regression model, to understand the causal impact. So another methodology is called synthetic control, where we actually create a control group where we don't have a clear control group to analysis. So we create a control group using AI techniques, and using that control group, we'll compare the treatment and control difference. And the instrumental variable, so where it's mainly used where we have a lot of confounding variables, and where we don't know whether we miss any confounding variable. So we introduce another variable called instrumental variable, and perform the regression analysis and understand the influence of that instrumental variable. Then if that influence is less, then we'll go with the normal regression models there. And the covariate adjustment is also another regression model, where we used, instead of confounding, we use the covariate, like that variable that only influence the treatment, and using that we model the regression. So that is called covariate adjustment model. And we have, if we have a complex network where we influence of today, the data of today may influence the data of future, and it's like a stochastic model, then we use models like Bayesian networks. And if we have a complex data and unstructured data, then we can even go with the deep learning models, where we can analyze the cause and effect. And all this advanced model needs more advanced machine learning AI techniques to solve, and like the analysis and analysis metrics also will be more complex compared to the econometrics models like propensity models and DID models. So let's go to a case study where we are using an example of bike sharing here, So all these are a synthetic data-based case studies. It's not a real data. So I'll go over the high level. So the case studies actually here is understanding, evaluating the impact of bike sharing program using a propensity score matching model. So the scenario here is a city implemented a bike sharing program to promote a sustainable transportation and reduce the carbon traffic congestion, also reduce the carbon emission in the city. The city wants to evaluate whether the program is significantly reduce the car usage among the citizens. So, however, the program was not introduced as a randomized control trial. The participation in the program on individual's choice, local proximity to the bike station, and other factors. So it leads to a selection bias. Since there is no randomized control, uh, uh, randomized participation here, so we can't use the randomized control trial to estimate the impact of bike sharing on the car usage. And also, it's on people's choice, so there is a selection bias. So we need to use advanced causal methodology to understand the effect of bike sharing on car usage. So, so directly the comparing car usage between people who adopted the bike sharing program, we can call them as a treatment group, and those who don't, we can call it as a control group. It might lead to a biased result because individuals are using bike sharing because some people are like more environmental conscious, some people are health conscious, and also because of that they uses the bike sharing program. And some of the reason, like it's maybe close to the workstation, it's maybe close to their home, that's why they use the bike. And also some of they don't have the car, they can't afford the car, or like operating a car is more uh, pricey, that's why they're using the bike. The income level, access to public transportation, weather also affect the car usage. So these are the external confounding factors that's affecting the usage of bike and usage of car in the city. So to overcome this bias caused by these confounding variables, we can use this causal inference techniques to like avoid this selection bias. So where we are using a causal model using propensity score matching. So high level, I'll go over how this matching is working here. So we have a set of people in a city where in that cohort of people, we are taking a subset of people who use this bike sharing program. And we call these people as a treatment group. And another subset of people who didn't use this bike sharing program. And we call these people as a control group. And what happened in when we use this machine learning techniques? So this machine learning, we use all the confounding variables that explained in the previous slide, such as their ages, their demographic, their income, the weather data in that area, also the location of this bike sharing data. All this information we use and we build a machine learning model. And this machine learning model generating a score, so that is a probabilistic score. And using the score, we matches that control group and treatment group. Users having similar characteristics, similar score, we match them in from control and treatment. Then we compare how their car usage is changed because of this bike sharing. So what is the difference between the car usage among the similar group in the control and similar in treatment, how it's different? And that will help, that estimate actually help us to understand the biased score for the causal effect of this bike sharing. So that is the high level, and we want to do so many tests to understand whether this model is good. We can use different evaluation criteria. I'm not covering all these details. I can share the like references for getting more into like when we do practically uh, on this thing, what are the things we need to focus, what are the accuracy metrics. I'm not going to cover all these things, but we need to check all that conditions to satisfy so that we'll get a good biased estimate. So I'll go over the steps that we need to do to get this causal estimate. So first step is to define the treatment and outcome. So where we define uh, who are the people who are adopters of the bike sharing and who are not the adopters of the bike sharing. And it's normally denoted as treatment T, and the value can be a binary variable. T equal to 1 for adopters and T equal to 0 for non-adopters. And the outcome is the car usage. It can be measured as the miles or the kilometers they drive, or the car frequency, how many times they use the car during that time window. Or we can also use like time they drive, or the how many trips they used, this kind of things as treatment. So depending upon like what are the data available or what is the easily what data we can collect easily, we can define our treatment according to that. We can define our outcome according to that. And the next step is to collect the observational data, where we collect the other confounding data such as like their demographic, age, income, their education, the job, then the geographical data such as bike sharing, whether it's an urban or rural residence area, and how many bikes it's available, what is the cost of that bike, and the other factors such as like pre-existing car usage, for what is their attitude towards the environment, whether they're like more environmental friendly person, that we can determine through a survey, and other factors such as whether public transportation details, all this data. So collect all this observational data and create a set of confounding variables. Once we have this treatment and outcome and confounding data, then the next step is to set up the machine learning model. Use machine learning model like any regression random forest model to estimate the probability of participating bike sharing program for each individual based on the observational data that we collected. Then using that model, we can the next step is to match the treatment and control group. So match the bike sharing users with non-users who has the similar propensity score. For example, if a person have a propensity score of 0.7, then we can match if control doesn't have a user who has exactly 0.7 score, we'll be matching most closest. For example, if the control group has a user have a propensity of 0.69, then we match with 0.7 with 0.69 users. And we'll ensure both control and treatment groups are comparable. Once we have that matched data, we'll evaluate our outcome, the differences. That calculate the difference in car usage between matched pair. For example, if we are going with the outcome as a reduction mile, then we'll identify the difference between the reduction that causes in control and treatment and compare that. And that we called it as an average treatment effect. And that's how the overall flow of like how a propensity score modeling will be used to determine the average treatment effect. So let me go over some code here, some Python code, high level. Yeah, if you're not familiar with Python, like don't worry, like this is just a like very simple code. I can share this code once the presentation is over. I can share both presentation and code. You can use a collab, Google Colab to run, and also there is no data used, like I use synthetic data. So you can like play around this kind of model and understand. So the first step is like where we can use important libraries. So these are called Python libraries where we needed for like creating this model, like libraries like I know you might not be familiar with the Python languages and the libraries, so don't worry about that. Like you just need to like copy paste this, import all the required libraries, and once we have these libraries, so these libraries have the information, the model, Python model that we can use in our uh, matching algorithm. So once we import this important library, the next step is like we are like I'm just running this code. So we are creating the data set where like it's synthetic data where I'm creating based on some random numbers, some random like data. For example, like people who has age between 18 to 65, some random numbers for their income, distance to station by station, their environmental score, whether they're like more prone to like more likely to have a high attitude towards the environment, then the car usage, uh, how much they use car before the treatment, and what is their bike uses, whether they use that bike sharing program or not. Then once we have that created that data, so in real life we need to collect this data. So for like simplicity, I just created this using synthetic data. And once we have the real life data for confounding variables, and once we have the data for outcome, so here I'm using the car usage, post treatment car usage as our outcome variable. Then I define these in a notation where X is the set of confounding variables I use for the modeling, and Y is the with the treatment data, whether they use the bike sharing or not. Once I have the confounding and treatment data, I can use any like machine learning model. Since this is a classification problem, I use a model called logistic regression, and the logistic regression actually fit the X, the confounding variables, to the Y value, the treatment value. Then it will give me a probability score of individual person, whether that person is likely to be used the bike sharing or not. Once I have this logistic regression score, I call it as a propensity score. Then I use this propensity score like to match the treatment and control. For that, I'm creating a two data a frame data set where I have the score for treatment group and I have the score for control group. So this is how the like a propensity score graph look like. I have a set of score for my control and I have a set of score for my treatment. Once I have the score for treatment and control, what I'm doing is like I'm using another machine learning model. It's called nearest neighbor for matching this control and treatment with the similar score. What this actually doing is like whoever have the close similar score which matches with the control and treatment group. And once we matches this user, then like we are like identifying like who the persons, the nearest individual. Then for them, we are identifying the difference between their post car usage. The difference between the post car usage is my average treatment effect. So here, based on this synthetic data, I'm getting an average treatment effort of 2.962 hours. That means because of the bike sharing program, uh, we are able to reduce the car usage by around 2.992 hours. Around 3 hour reduction is happening due to this new bike sharing program. And like we can visualize this, the treatment car reduction, and also we can also get some estimates about the confidence interval, how well it is. I'm not explaining all other statistics here, but this is how high level it will be. And also we can confidently say that this reduction is actually caused due to this bike sharing. So no other factor is causing the bike sharing. New bike sharing itself is causing this reduction. So that is the high level on how we can use the Python for like using understanding this propensity score modeling. So coming to like some of the challenges, the main challenges that normally faces is the data limitation. So basically like collecting the data, there will be like a lot of missing data, handling that noises. So because of that, like our analysis can be biased. So that we need to handle before like processing the data for modeling. And also some cases like we won't get the fine granular data. So for example, like in the case of bike sharing, we won't get the granularity at the user level. We may have the granularity for the distance to the bike station. We won't have maybe exact location of the user, so we can't get the distance to the bike shore. So that is the one issues like lack of fine granularity, and that also sparse our data, and that will skew our result or bias our result. So another challenge we have is the confounding factor. So like we can't always measure all the confounding factor. There might be some hidden factor that we can bias the results. And also the complex interaction between each confounding factor that may bias our result. For example, the impact of weather on traffic flow and road accidents. So the road accidents also, if we are like using outcome as a time, then the road accidents also may impact the time of the traffic. So that's another factor like that has some serious correlation that affect bias our results. Then the model complexity, model interpretability. If you're using like advanced models such as deep learning models or Bayesian models, Bayesian and causal inference models. So all these models are like a black box. So like it lacks the interpretability. So that may complex the art analysis, and also and because of the lack of interpretability, it may lead to trust issues. So it's difficult to validate the causal insights for policy decisions. And another issue is the scalability and generalizability. Maybe this particular model will be suitable for this particular city. It may not be suitable for another city. So it can be generalized overall, like overall in this state, this is the best strategy. That we cannot generalize unless we need to create a different model for different locations. So that is one issues. And another most important one is the ethicality and practical constraints. So because AI-driven policy may have unintended social consequences. Because some of this data may be privacy-related data, and collecting that and processing it that may be used concern. And also the mobility data, collecting that and processing that also cause a privacy issue. So we want to validate all this ethical standpoint of view, whether that is like legal, is it trustworthy, all this need to validate before doing something and before implementing something. So that is like high level challenges that we need to keep in mind before getting into solution and before reporting that answer. Some practical best practices, some suggestions for best practices. So first one is to like understand the domain and context. So whenever we building a solution, whenever we building a problem, understand the domain, uh, connect with a domain expert and define the problem correctly and clearly so that like we will be aligned, and also understand the real world goal, whether how it's affecting, what is the other factors. If we are not introducing bike lane, what is the reason between the introducing, what are the objective of that, and what are the things that's affecting. So all this domain knowledge is important in context of this causal influence. And also understand, practice the robust data practices, understand the data well, clean the data, process the data to ensure the high quality data that we are using. Otherwise, like as I mentioned earlier, it may lead to a biased result. And also using different, if we have unbalanced data, using different balancing technique to balance the data. And the next is the leverage interpretable model. Like I mentioned earlier, like some models are not interpretable. So there are like different AI techniques now available. It's called explainable AI, where we can use to interpret data so that it can be translated to the common people who are not like not knowledgeable on this domain. So that kind of techniques we can use to translate the knowledge to other people. And also like presenting the policy impact to a decision tree. So like there are different explainable model and visual model. So use that things wherever available so that it can be more interpretable. And also the one important things when we use causal inference is doing robustness check and sensitivity analysis, so that like we can ensure that there is no other confounding variable that affecting our results, and it's help to validate our results with multiple methods and multiple data so that we'll showcase a consistent valid results. For example, like there are like different models where we can use synthetic control and double model, or some of these models are like cross validated model, which will give more confident estimate of our treatment effect. And another thing we need to keep in mind is, I already mentioned, like incorporate the ethical and privacy consideration. If there is a privacy policy available in that region, what is the ethical practice? So consider all these things before like giving any causal conclusions. And also use iterative models, validate the results, like build a small model first initially, then scale it up, like build a pilot model, then scale it up, and deploy dynamic practice, making the practice result in a selected area to evaluate effect. So rather than building the model for entire area, like choose a subset of area, then build the model, validate, then like generalize it. And finally, the communication of the results, uh, findings to be clear and actionable. So whatever the findings that we can provide using causal inference, it make sure it should actionable manner for decision making, and it can give some value to this thing. Oh, and also use some dashboarders visualization techniques so that they can understand what what we are telling, and it helps like getting the clear insights. Yeah, that's like all I have today for related to causal inference. And you can get, if you are interested in more about learning causal inference, I am having a lot of good recommendation here. Some good books on causal inference by Scott Cunningham, and some books from Judea Paul, causal, if you are interested in causal inference for social and biostatistics. There is books for causal inference for statistics. And if you want to understand the impact measurements, there is a mastering metrics books where we can understand the cause and effect relationship. And if you don't have times to go for the books, then there are like good paper articles. And if you want to know more in detailed depth of each individual method, like there are like different courses, and there is open courses from MIT that's free. You can like take at your space. So these are some good materials that's available online. Yeah, open to questions if you have. Anyone have any questions?
Participants, if you have any queries, you can ask in the chat box, or
Or you can reach out me in LinkedIn, like if you have any questions. I'm happy to answer.
okay, Athulya, if they have any questions, I'll forward it to your mail.
Yeah,
Thank you for the wonderful session. Also, I would like to appreciate the time you dedicated to preparing such a comprehensive presentation. It was very amazing. Thank you for the support.
Thank you all. Yeah. Have a great day. Bye.
Participants, we can close the session now. We'll meet tomorrow. Thank you.